Back in Unit 6A, we learned to draw Lewis structures for molecules. Here we're taking a look at the Lewis structure for the water molecule on the left, H2O, and the carbon dioxide molecule on the right, CO2. We learned in Unit 6A that water is a liquid at room temperature because water has strong dipoles pointing from the hydrogens to the oxygen due to oxygen's high electronegativity. Oxygen being 3.5 and hydrogen being 2.1, there's a difference of 1.4, and we said that that would give rise to one of the strongest intermolecular forces, dipole-dipole forces called hydrogen bonding. This hydrogens become partial positive, oxygen's hogging each of these electrons of hydrogen, so it becomes partial 2 minus. We have a strong dipole going this way. If you take these two dipoles and add them up, we would have a net dipole resulting. So it's almost like if oxygen was a car and we have somebody pushing oxygen from this side and from this side, oxygen's going to end up going straight up the top of the paper. That's what a net dipole is. A net dipole is when we have two dipoles which can be added up to create a net dipole. So on our water molecule, if we add up the two separate dipoles, our net dipole would be pointing towards oxygen in this direction. That means the oxygen will be partial negative or 2 negative, and this area of the water molecule is partial positive, and that would allow two nearby water molecules to attract one another. So if another water molecule gets near this, the top water molecule, this oxygen on the lower water molecule is partial negative, this area on the upper water molecule is partial positive, so these two molecules would stick together as we learned in 6A, making water a liquid at room temperature. The sticking is pretty strong. It would actually be called hydrogen bonding because the hydrogens are attached to a highly electronegative element. In this case, oxygen. The highly electronegative elements are fluorine, oxygen, and nitrogen. When hydrogen is attached to a fluorine, oxygen, or nitrogen, and there's another fluorine, oxygen, or nitrogen near it, we get a hydrogen bonding between the two molecules. It is a strong dipole-dipole attraction. But that gets us to another question. Carbon dioxide is not a liquid at room temperature. Carbon dioxide we know is a gas. We're exhaling it with every breath. Carbon dioxide also has a relatively strong electronegativity difference between oxygen, which is 3.5, the carbon, which is 2.5. The difference is 1.0. Why don't two carbon dioxide molecules stick together when there's a large electronegativity difference? Well, as we're going to learn in Unit 6C, there is more to molecules having net dipoles than just having differences in electronegativities which fall under polar covalent bonding. When there's large difference in electronegativity, not a huge difference. If there's a huge difference, like a metal with a nonmetal, it goes fully charged. But when there's a large difference, two nonmetals, one weaker than the other, giving rise to an electronegativity difference, we get polar bonds. Why on the water molecule do the polar bonds give rise to an intermolecular force where they attract? Whereas on CO2, there are polar bonds, but two CO2s do not attract. And that's what we're going to get to in Unit 6C. We can see from the CO2 and the H2O example that polar bonds alone do not give the molecule immediate dipoles. So there's another factor that comes into play. In order for a molecule to have a net dipole, not only does it have to have polar bonds, but it has to have a specialized shape, or a special shape, which we call asymmetrical. So what we're getting into now is the fact that molecules have shapes. The valence shell electron pair repulsion theory, often abbreviated VSEPR or VSEPR for short, is a theory where we can predict the three-dimensional shape of a molecule by analyzing what is on the molecule, namely the central atom. So the valence shell electron pair repulsion theory, or VSEPR theory for short, is a theory which will enable us to take a two-dimensional Lewis dot diagram or Lewis structure and determine its three-dimensional shape. When we know what the three-dimensional shape is, and we know what types of bonds, polar or nonpolar, are on the molecule, we then can more accurately predict the physical properties of that molecule. So what is it that determines the geometric shape of a molecule? Well, there are two things that we have to look at. First, we have to designate the central atom of the molecule. The central atom, as we learned when we were doing Lewis structures in 6A, is the atom that we're building the molecule around. It's the one that needed the most bonds. We can predict the shape of a molecule with respect to the central atom by counting the number of things, as Tyler DeWitt would say, that are on that central atom. The things we are going to count on the central atom are the number of bonded atoms, which we abbreviate with the letter B, as well as the number of lone pairs on that central atom, which we abbreviate letter E. So we count the total number of things. The things is a very simplified name for what we call the steric number. The steric number is the number of bonded atoms on the central atom, and we add to that the number of lone pairs, not lone electrons, but pairs of electrons that are on the central atom. Again, the central atom is the one that we put in the middle. So A is the abbreviation for the central atom. B is the number of atoms bonded to the central atom, and E is number of lone pairs or unbonded electron pairs. It's important to realize that we are counting bonded atoms. So when we're looking at how we are going to determine the shape, we're going to count the total of number of things on the central atom. When we count atoms, we're counting bonded atoms. We are not counting the number of bonds that the atom has made to the central atom. And then when we're counting electrons, we're counting pairs of electrons. We are counting each pair as one. We are not counting each electron in the pair, which would be two. So a pair counts as one. Why do the pairs have an influence? Why do we care about the number of electrons when we're looking at the shape of a molecule? It's because the lone pairs of electrons actually repel better or more strongly than the bonded pairs, because the lone pairs are free to move, free to spread out, free to repel better. The electrons that are in the bonded pairs are restricted between the atoms. So lone pairs push better and distort the shape or symmetry of the molecule. So lone pairs have a dramatic effect on the atom. That is why when we were learning to do the drawings, we said make sure in Unit 6A to put all the lone pairs on there. When there are lone pairs on the central atom, it can make this can make the molecule what we call asymmetrical, which is not having the atoms distributed evenly. When there are no lone pairs, the molecule is symmetrical for the most part. When we're talking about symmetry, it means that the atoms are spread about evenly. So symmetrical molecules have the atoms that are attached to the central atom spread about evenly in the space surrounding the central atom. Asymmetrical molecules do not have the atoms spread about evenly in the space surrounding the central atom. And that's what it says right here. Symmetrical, everything's evenly distributed in the three-dimensional shape. Asymmetrical is not evenly distributed because the lone pairs push better than the unbonded pairs, which gets the molecule out of shape or asymmetrical. Again, the great value of the valence shell electron pair repulsion theory is it gives us a way to take a look at the three-dimensional shape. And when we know the three-dimensional shape, we can better determine if the molecule is polar or nonpolar. Polar molecules have net dipoles and stick together better. Nonpolar molecules do not have net dipoles. They do not stick together as well. It affects all sorts of physical properties, including what state of matter a molecule is at, whether the molecule is soluble in other molecules or solvents, whether the molecule will be capable of dissolving other things. It determines things like melting points and boiling points, for that matter, viscosity, how well molecules flow. So nonpolar molecules, once again, will not have lone pairs. In order for a molecule to be symmetrical, it will not have lone pairs of electrons on the central atom because those lone pairs push better and distort the shape into asymmetrical. So nonpolar molecules, as we mentioned, will be symmetrical, which means the atoms will be evenly distributed around the central atom, and there will be no lone pairs to push them into the distorted shape. When this happens, a very interesting thing occurs. The polar covalent bonds cancel out. Let's take a look at why. Carbon dioxide, as we mentioned, has carbon and oxygen. The difference in electronegativities is 3,5 minus 2,5, which is 1,0. Oxygen is trying to hog the electrons. But this molecule has carbon as the central atom, which we would call A, and it has an oxygen and an oxygen on it. There's two bonded atoms and no lone pairs to bend this into a distorted shape. So let's see what would happen to the dipoles. These oxygens are trying to pull the electrons. They're trying to hog them. They're trying to be polar. But this oxygen is pulling directly to the right. The other oxygen is pulling directly to the left. If you have two oxygens pulling equal and opposite each other, these little dipoles cancel out. No net dipole would result. This molecule is symmetrical. The dipoles canceled out. There's no net dipole. This molecule ends up being nonpolar because there's no net dipole to arise from the little dipoles on the molecule. Asymmetrical molecules do have lone pairs of electrons that bend the molecule into a distorted shape, which we call asymmetrical. Asymmetrical molecules can have a net dipole if they have polar bonds. So what do we need for a polar molecule? For a polar molecule to exist, the molecule has to have polar bonds, which give rise to little tiny dipoles. And if it's asymmetrically shaped, the little tiny dipoles will not cancel out. How can we tell if a molecule is going to be asymmetrical? A safe thing to look for is lone pairs on the central atom. Here we have a water molecule. We know water molecules have a strong net dipole. We mentioned when we started it's because there's a dipole going from one hydrogen to the oxygen and another dipole going from the oxygen or hydrogen on the right to the oxygen. This molecule down, the water molecule, would be asymmetrical. First hint is these are lone pairs right here. These lone pairs bend the hydrogens down. Why is water not linear shaped like the carbon dioxide? Well, this is symmetrical. We have an oxygen here and an oxygen here, and they're directly opposite each other. They're evenly distributed in the space surrounding the carbon. On a water molecule, the hydrogens are not evenly distributed. We have one down here, one down here. We have no hydrogens at the top. It's asymmetrical. So what happens then is this dipole cannot be canceled by that dipole, and instead they add up to a net dipole. The B on this molecule is 2. The E on this molecule is also 2. There's a lone pair. There's a lone pair. Lone pairs can make the molecule polar if there's polar bonds like we see on the water molecule. In our next video, we'll take a look at what the names are of the different shapes.